Okay, so the big topic that we'll be talking about in kinetics is reaction rates. Now, you guys can probably tell by the actual term, it's just how quickly or how slowly a reaction will take place. So the speed of a reaction, that's what a reaction rate is. Okay. So the speed at which a reaction takes place is called the reaction rate. And so I got some nice pictures for you down there. Since I am Korean, I did put some things that go boom. Because it's also a very good way for us to imagine some reactions that go very quickly, right? So for example, we got a bomb. Bombs go off in a very short amount of time, and that's why there's a lot of there's a lot of force because the gas molecules are heated up very quickly. They accelerate very quickly, and so explosions have a very quick reaction rate. Some of them go 0.001 seconds, some slower ones, 1 second. But then we also have some other reactions that take a very, very long time to take place, right? One good example is rusting. When iron is oxidized, it reacts with the oxygen in the air and it creates rust, like this rust on this boat right here. It could take about 30 years, right? So it's a very slow reaction. And then we have some reactions that take millions of years. So like the breaking down of rocks and minerals and things like that, when they react with air and with water, that can take a really long time. Okay, so that's kind of what we're talking about. Obviously, we're not going to be talking so much about these super long reactions, but just keep in mind reaction rates can vary significantly. Yeah. Erosion is not a reaction. It's the weathering. It's a physical change. But as erosion takes place, some chemical reactions do take place as well, as like some of the minerals underneath the surface are exposed. They'll react with water and with air and things like that. Yeah. Good example is gallium. I don't know if you guys know gallium. Gallium is a compound that we use to make like solar panels, and we got to mine it out of the earth. When you separate gallium from a rock, it'll expose some of the gallium and it'll react with the air and it creates this toxic gas. And so a lot of gallium miners get these crazy lung problems. So yeah, anyway. So what we'll be looking at in this unit is the step-by-step molecular level view of how reactants go to products, and that's called the reaction mechanism. So basically, how do the actual compounds, because we know how to do like stoichiometry, right? We know that if we have hydrogen gas and oxygen gas, it can make water. But in this unit, we'll be talking about how they actually form water. So what they actually do. It's not as interesting as it sounds. They just bump into each other. Okay. All right, and that's what kinetics is. Kinetics is just talking about the reaction rate and how they bump into each other. All right, any questions about the starting definitions? That's chilling. Okay. All right, so like I said, basically the way reactions happen is the molecules have to collide with one another. Okay, molecules are very dumb. They're like stupid people just bumping into each other, and that's what causes these reactions to take place. So the key concept you need to know is the more these molecules collide with one another, the higher the reaction rate. Okay, so I'm going to take it back to dating again. If you want a reaction to take place between you and somebody that you're interested, right? You're going to have to not collide with them, but bump into them more often, right? Like, gentlemen, if you want to talk to a lady and have a reaction with her, right? You can't just be like not seeing her, right? You got to find ways to bump into her in the hallway. Maybe take some of the same classes. Maybe you're at the same cafe. Now, you don't want to be too creepy, but you want to have more interaction, right? And so we increase the reaction by, texting them sometimes, liking their posts, right? Anyway, you guys know how it is. That you got to increase the collisions, the interactions, to increase the rate. Okay. Of course I texted her. Yeah.
So that we should like explain that on the AP test.
Yes, exactly.
Yeah.
Molecules are stupid.
They're stupid. You want to humanize them.
Yeah.
AP test really use like a real life example.
No. Yeah. You want to talk about the chemical properties? No, you're good. What's up? If you want to be funny, yeah, but you're not gonna get points for it. Yeah, you wanna be as clear and short and concise as possible. So you're gonna talk about the properties, the chemical properties, not any like you're not gonna be like such as. You don't want to make an analogy.
So what are the examples?
Yeah, I'm just doing this to help you guys understand it better, but don't do this on the AP test. Yeah.
Imagine though, if we were like, our chemistry teacher says that when it's like trying to kill people,
You do.
we should, like go at a higher rate.
You do.
Like,
Yes, don't say
would
that
they
though.
like search you up?
No, they wouldn't. Okay, so there are 4 things that determine reaction rates. Number 1 is the physical state of the reactants. So here I have a picture. Basically, reaction rates are limited by the area of contact between the reactants. So the more space there is for the 2 compounds to interact with each other, the faster the reaction will go. So good way to think about this is if you guys have ever put a sugar cube in water, it takes a while to break down, right? Because it's a cube. There's only so much area, surface area for the water to interact with the sugar. But if you put powdered sugar, it dissolves a lot quicker, right? And it's because it's powder, there's more areas for the water to react with. Okay, so powdered medicine dissolves in your stomach and is absorbed more quickly than something in a tablet. Yeah.
So does that mean liquid and water or liquid and gas react?
Yes, absolutely. Which is also a reason why we dissolve compounds into solutions, is to increase the reaction rate. Yeah. Good observation. Okay, so we got a picture right here. Again, these red things, they can only touch the green, the molecules on the outside of the solid. The inside ones aren't being touched by the other reactants, right? So it'll take longer for it to go. Okay. So that's the first factor that affects reaction. All right, second is the reactant concentration. Okay, and this should be pretty self-explanatory. The more reactants you have, the faster the reaction will go. Okay. So I actually ran out of steel wool last year. I usually do this, but I don't have any. But if you have steel wool and you just have it out here, it's not gonna burn, right? But if you put steel wool into a container that has 100% oxygen, it will spontaneously combust and it will react with the oxygen. Okay, so the more oxygen you have, the faster the reaction will go. Okay. So higher concentration, faster reaction rate. I have a dating example for this one. Do you guys want to hear it?
Yes.
Okay. Higher concentration, okay? So let's say that you are a dude, right? You're very thirsty. Okay, and let's say the concentration of ladies in your school is 1. You only have 1 lady. Okay, it might take a little bit longer for that reaction to take place, right? However, let's say we increase the concentration of ladies at your school. Okay. Okay, and let's just assume, obviously this analogy isn't perfect, but let's just assume these ladies don't know about each other. So the thirsty guy slides into her DMs, I know, not good. But the more DMs he slides into, the higher chance he has to have a reaction, right? So same thing, you increase the concentration of one of the reactants, the faster the reaction will go. I do not endorse this type of dating strategy. Like I said, he is thirsty and desperate and that relationship won't go well. But if the goal is to just have a reaction as fast as possible, you want to increase the concentration, okay? All right, am I being recorded? I got recorded, huh? I do. It's all good. Again, I do not endorse this dating strategy. Okay, next one, reaction temperature. Now we know that when you increase the temperature of a compound, it's gonna make the compounds move faster, right? And so the faster it moves, the more energy it has, the higher chance of the reaction going more quickly. Okay, so a good way to think about this is the chemicals inside of milk right? If you put them in a fridge, it takes a long time for them to degrade and spoil, right? Or a longer time. But if you leave milk outside on 105 day, that milk's gonna turn nasty real quick, right? And it's because the compounds are reacting faster. They're degrading faster, okay? So those are 3. And then the last one is if you got a catalyst, it will also increase the reaction rate. We'll talk about catalysts more later, but just keep that in mind, okay? All right. Any questions on the 4 factors? Yeah, son.
We're not supposed to adopt this.
Yeah.
Actually, not the house is company that's kind of straight away from that. And I was really happy. But now.
That's not good. I don't want you being happy.
We're reaching the units where you're not happy yourself either.
I don't like this unit either.
I don't think we like them.
I don't really like chemistry that much, but it pays the bills. I'm just kidding. Chemistry is fun.
We're gonna have a lab this year.
No, next unit. All right. So, I am going to put 11.1 up here. I want you guys to answer this question. See if you guys can explain it in 1 sentence. Okay. Your past test, you guys wrote me novels, and it was great. I loved reading your writing. Some handwritings were better than others.
Okay, stop.
I didn't say anything about you. Why are you getting defensive? Okay, but I didn't say any names, okay? But I want you guys to try answering 11.1 as concisely as possible, okay? So I want you guys to try answering this in 1 sentence, using the information that we learned, okay? So which of these vessels will have the fastest reaction rate? You can just label them as 1, 2, and 3, and then we're gonna assume they're at the same temperature. Okay, let's take about a minute to do that. Alrighty, guys, so let's go over the answer for 11.1. So first and foremost, let's talk about which one has the fastest reaction rate. Which one do you think is the fastest? 1, 2, or 3?
2.
Yeah, 2. Good. Now for your reasoning, should be as clear and concise as possible. First thing you want to mention is that it has the most area of contact between reactants. And then the second thing that you can say is what else? Yeah, reactant concentration. Okay. So if you compare 1 and 2, right? 2 has higher area of contact, and then you can compare 2 and 3, and 2 has a higher reactant concentration for both the red and the blue ones, and so those are the 2 reasons. So you can write 2 because it has the most area of contact between reactants, and the reactant concentration is the highest. That's it. Do you have a question?
I was just gonna say, like, it's like distinguished, like, the same but it's area because I don't know, yeah, like 3 area.
2 technically has the most area. You just need to talk about the correct answer. Yeah.
Like, so you just have to like name the big stuff, like explain exactly why.
Yeah, as long as you hit the main points.
There's like 8 of these instead of 4.
Yeah. Yeah, you don't need to go that detailed.
Okay.
Yeah. So. Only if the question asks. So like if the question says like to list them in terms of like highest to lowest, then you would have to. But if it asks which one's the highest, just give the highest. Yeah. Yeah. I mean, you're not going to lose points for doing that, but it's not mandatory to add all that information. All right. Any other questions? Alrighty. So let's move on. So I'm going to give you guys about 3 minutes. I want you guys to take a look at 11.2. Now there are 3 different parts to this question. And again, I want you guys to practice a little bit writing your FRQ answers. So these are their own individual sets. So don't compare like 1 and 3. Just compare 1 and 2 and 3 and 4 and 5 and 6. And I want you guys to go through all 3 sets and to answer the question of which one do you think will have the faster initial rate of formation of CO2. Okay, so take a look at these charts. See if you guys can interpret the data on this table. And then write your responses for A, B, and C, and then we'll go over them really briefly, and then we'll move on to the next section. Okay, so take about 3 minutes to do that. The right answer. Alrighty, so if we take a look at part A, which one do you guys think is faster, 1 or 2? Yeah, I heard 2. 2 is faster. Why is 2 faster? Yeah, higher concentration. That's it. Okay. Let's go to number 3. Which one is faster, 3 or 4? 3. Why is 3 faster? Yeah, higher area of contact. And then you could say, yeah, if you want to clarify, you can say powder has a higher, yeah, whatever. Okay, and then last one for C, 5 or 6? 6. Why is 6 faster? Yeah, higher temperature. That's it.
So why is a higher temperature like? make it faster?
Yeah, higher temperature speeds up the reactions because the molecules are moving faster. And so if something is moving faster, it has a higher chance of making contact more frequently, and it also has more force. And so it can basically force the other reactants to react with it. What's up?
So would we literally like understand by that as we do it?
In a sentence. Yeah, I just don't want to type too much.
We just want to slow it why, or can we just say?
No, you can just explain it like this. Yeah, higher temperature. All right, so hopefully that wasn't too bad. Now we're gonna start doing the maths with this. Okay. All right, maths. So reaction rates, the way that we describe them, the unit of measurement basically is gonna be molarity per second. So if you guys remember molarity, molarity is equal to moles over liters. Oop, not seconds, liters. And so we describe reaction rates with molarity per second.
Wait,
Yes,
so do we put stuff in the fridge so that the reaction of that
slows down.
slows
Exactly.
down?
That's why we put it in the fridge. Yeah.
What?
Okay, so if we want to write the unit of measurement for reaction rates a little bit or more complicated, since molarity is moles per liters, you can write moles per liters per second. Okay, that's another way that we can describe it. Okay. Hey, good luck. No, winning is everything. The most fun thing is winning. Just kidding. All right, so we're gonna take a look at these flasks down here. Now, I know that there are red balls and blue balls, and everybody laughs when I say blue balls, but please don't laugh, okay? I just need to clarify that because every time I read this scenario, everyone starts giggling, okay? But look at the image below. The red balls are compound A and the blue balls are compound B, okay? And we're gonna assume that this is the same system, but at different time periods, okay? So this one right here is at time 0. This is at 20 seconds, and this is gonna be at 40 seconds. So the red balls are turning into the blue balls, okay? I know, get it out of your system, okay? So when we have a system, you guys all right? So if you guys take a look down here, we got some numbers for the system over time, right? First we have 1 mole of A and no moles of B. And then slowly, if you guys notice, what is happening to the moles of A? Is it increasing or decreasing? Yeah, decreasing. So the concentration of A is decreasing, whereas the concentration of B is increasing, right? This is what happens in a chemical reaction. The amount of reactants decrease because they are being used to produce the product. So A is being used to make B, okay? Now, given this information that we have, what we can do is we can calculate the rate or the molarities per second in which A disappears and B appears. Okay, so there are 2 rates going on, A disappearing and B appearing, okay? And so the way that we can calculate that is using this formula right here. The average rate in a reaction is going to be delta, so the change in the concentration of something divided by the change in time. Okay. So the average rate can be calculated by dividing the change in concentration by the change in time. And we always go final minus initial. Either the disappearance of A or the appearance of B. So the average rate of the change in molarity. Alrighty, guys, so we're gonna do 11.3 together. Now, I have the question up here, but if you have the workbook up on your Chromebook, you can take a look at the picture. That'd be a better way for you to refer to the numbers. Okay, but what we're gonna do is we are going to calculate the average rate at which A disappears from time 0 to 40 seconds. Okay, so the average rate of disappearance over that time period. Okay, so what we got to do first is if we want to find average rate, so average rate, we're going to just use this equation, okay? So we're going to figure out first what the final time is and the initial time. Okay, so what is the final time here? Yeah, 40. 40 is the final time. So I'll write TF, not that TF, but okay. And then what is the initial time? Yeah, 0. So that'll be TI. Okay, not the wrapper. Okay, so we got TI and TF. Okay, so we can actually do the bottom of the fraction, right? We just need to do TF minus TI. So 40 minus 0 is 40. Yeah, super simple. The bottom is very easy. All right, now we just need to find the molarity at the final time at 40 seconds and the molarity at the initial time, 0 seconds. So if we take a look at the picture, let's find the molarity of A at 40 seconds. Okay, so we know that molarity is moles divided by liter. So how many moles of A are there at 40 seconds? How many moles of A? Yeah, 0.3. There's 0.3 moles of A. Okay. So we're going to do 0.3 and it's 1 liter. So the molarity is going to be 0.3 molarity. So at 40 seconds, there are 0.3. Whoa, why is it so fat all of a sudden? 0.3 molarity of A. Okay. And then we can subtract it by the molarity of A at 0. How many moles of A are there at 0? 1. And so 1 divided by 1 liter would be 1 molarity. Okay, so I want you guys to pull out your calculators. I'll give you guys about 30 seconds. See if you guys can punch this in and see if you guys can write the average rate properly. So give me the units of measurement, give me the sign, and yeah, let's see if you guys get it.
This
These are the final answers.
I know. Yeah, no, I agree. I just like
Right on there. Mr. O says right neater.
yeah, right either.
Yeah. Try illegible.
Mr. O,
Yes.
if you say the rate of disappearance, it's not negative, right?
No, but you're asking for A and A is disappearing.
Yeah, so she's saying, yeah, you can say whatever the answer is, molarities per second disappearing.
Yeah.
Yeah, or A is disappearing at this whatever molarities per second.
Yeah.
Yeah.
You're not gonna say A is negative.
Yeah. Mhm. But then if you just wanted to give me the number, then you would have to give me a negative.
Okay.
Yeah. All right, so for your answer, you guys should get 0.0 or negative 0.0175 molarities per second. Okay. And since the rate is a negative number, that means it's losing 0.075 molarities per second. So this is the same thing as A disappearing. So if you guys know that a compound, the molarity is going down, then it should be a negative number. And if you know that something is being produced, it's going to be a positive number. Okay. That's it. Just make sure you guys keep that in mind. Yes, correct. Yeah. So we don't use meters very often, so you can just make sure it's capital M, and we know it's molarity. Yeah. Molarities per second, moles per second, molarity per second, capital M. Yeah, so if you take a look at the picture, here we have a certain concentration, right? 100% A, right? That's the concentration, 100% A. And as we go over time, the concentration of A is disappearing, right? So the exactly, yeah, it's being converted into B. And so as it's being converted, once A is converted, it's no longer A, right? So the concentration of A is going to go down. So here it's like maybe around, looks like 54%. And then here it goes down to 30%. So the concentration keeps changing over time. Yes. Yeah. Well, it has to do with the amount.
But it's still like the same amount of everything.
Yeah, everything is the same, but it's changing to something else. Exactly. Yeah.
So, is the like rate of change, does it kind of like, is it exponentially decreasing?
So that's what we're gonna get into right now. So yeah, like Robbie insightfully told us, rate changes with time. So unfortunately, these chemicals are very disagreeable. Okay, it's not like if it has a rate of change, it stays at the rate of change. So easy way I like to think about it is like, if you guys ever seen people sprinting, like Olympic sprinters or maybe people in track sprinting, if you guys notice in the very beginning, that's when they're the slowest, right? They start off from zero, no movement. And as soon as the gun goes off, they start running. But in the first couple seconds, they're still accelerating to their top speed, right? And then at a certain point, that's when they get to their top speed. But then after they get to their top speed, they either taper out or they start coming back down, right? And so same thing with chemicals. A lot of times the rate at which the molarity changes will change over time. Okay, just like how a runner's speed will change over time, their ability to accelerate will change over time. Same thing with these chemicals. And we'll look at how to do that right here. But first, I want you guys to try solving this problem, 11.4. Got a table for you guys to interpret, a lot of numbers. And I want you guys to find two different average rates. Okay, I want you guys to find the average rate from 0 to 100 seconds, and then from 300 to 400 seconds. Okay, so take about 3 minutes to do that. Just find those two rates. And then after that, if you want to answer the question of is the rate increasing or decreasing, you can try that on your own. Okay. But the point of this problem is to show you guys that rate does not stay the same throughout the whole reaction. It can change over time. Okay. Okay, so if we take a look at 11.4, we want to find the average rate of what is it? The reaction between 0 seconds and 100 seconds. So same thing, we're just going to use the formula that we used earlier. So I'll write average rate. Okay. So we want to go from initial or to final from initial. So we're going to use the time 100 seconds minus 0 seconds, which is obviously 100, but we'll just write it just for clarity's sake. Okay, what is the molarity at 100 seconds? Yeah, 0.082. It's right here. And then the molarity at 0 is right here. So it's going to be minus 0.1. Oh, molarity. Okay, so your rate of change right here will be negative 0.00018 molarity per second. Okay, everybody got that? Okay, so that means that the concentration of C4H9Cl is disappearing at this molarity per second. Yeah. Is it really? Oh no. Oh, thank you. Wait, why? How is it overflowing? I don't know. I guess the machine goofs. It's okay. I got it. Leave it. It's fine. As much. Thank you for caring about my coffee. Yeah.
So at 1 second.
I got it, Nick. Yeah.
It's decreasing that much.
Yeah.
So it's like constantly.
No, over this time period, over this time span, between 0 and 100 seconds.
So like each second, like if the rate goes down.
Yeah. Yeah. Or that's the average change from 0 to 100 seconds. Now between, like between 1 second and 2 second, it might be different. 2 second and 3 seconds might be different from 51 to 52, but just over this time period, that's the average rate of change. Yeah. Yeah, no constant, exactly. Yeah, just like a runner, right? They're not going to be at a constant change. It's always going to fluctuate a little bit. Same thing. Yeah. All right. Now let's go to the average rate between 300 and 400. Okay. So the average rate of change between 300 and 400, same thing. We'll do 400 seconds minus 300 seconds. And then for the molarities, we'll do 0.0448 minus 0.0549. And that should give you a final answer of negative 0.000101 molarity per second. Okay. So if you guys notice, is the average rate increasing or is it decreasing? It is decreasing, right? That means that the disappearance is slowing down. So between 100 or 0 and 100 seconds, the first 100 seconds, it is disappearing faster than it is between 300 and 400. Okay. Does anyone want to take a guess at why the disappearance rate slows down later on?
Well, I'm guessing as there's less and less like things to react with, like the reactants are disappearing.
Yes.
And there's less and less reactions.
Yeah.
And as we learn.
But yes. Yes. Yeah. Basically, the reason why the rate of reaction decreases is because as you go over time, the concentration is also decreasing. Okay. The concentration is decreasing. So remember how we learned that reaction rate is dependent on concentration, right? If the compound starts to disappear over time, there's going to be less and less for the reaction to go. And so it'll disappear over time. That's why the reaction rate slows down. Okay. I know you did. Yeah. Both of you ladies. I saw it in your eyes. Okay. Yeah. Vivian and Val both raised their hands, but you raised it like half a second faster. Yeah. Your reaction rate was faster. Whoa, there's levels to that one. Oh, shoot. Okay. Let's move on. Okay. So I know you guys love stoichiometry. And so we are going to talk about stoichiometry. Now, I don't want you guys to write this super long equation stuff because at the end of the day, what you want to think about in terms of reaction rates is that different compounds in a reaction will appear and disappear at different rates. Okay? So different compounds will disappear and appear at different rates, and that's going to depend on the mole ratio. Okay? So I'm going to write that down just so we have it written. Okay? But the concentration of different compounds in a reaction will be different. Okay? It's going to depend on the mole ratio. Take a second to write that down. And then after that, we'll do a quick question together. Okay, I'll leave 11.5 up there, but I want you guys to use this information right here where we said the rate of change depends on the mole ratio, and see if you guys can use that to solve 11.5. Okay. Supposed to be just 230.
Maybe like it's not.
Yeah, or the machine probably. Coffee is more important to me than any student. What's up? Yeah, go ahead.
Okay. Low calorie or protected. What about a little pro?
So for like the molarity one, it's like a part one and a part two. I just like
Let's put in the points, yeah, add them up. Alrighty, guys. So, if you guys copied that down, then we're gonna start the problem. If you guys started the problem and want to finish on your own, you can just ignore me and just check your answer at the very end. Okay. Okay. So we are going to take a look at this reaction right here, and it's telling us the rate of decomposition of N2O5. This guy right here is 4.2 times 10 to the negative 7 molarities per second. So I'm gonna write that down. So I'm gonna write 4.2 times 10 to the negative 7 molarity per second. Okay, and this is for NO2. Okay, now since it's disappearing, we got to make sure that we put a negative sign. Oh, actually, no, sorry. No, we don't. My bad. That's only when we're describing it. My fault. Okay, and then from there, we want to find the rate of, my gosh, I'm off my game. I wrote the wrong formula. My bad, guys. Okay, that's for N2O5. Sorry about that. I know, I'm just so stressed about my coffee spilling. Oh, such a waste. I had to throw some out. Such a waste.
We're stressed about 80 counts. So.
Oh, well, okay, there's levels to this, and my problems are a lot bigger than yours. Okay, I spilled coffee today. Anyway, so we want to figure out now the rate of appearance for NO2. Now, we said we're talking about the mole ratio, so all we need to do here is multiply the mole ratio of disappearance of this guy and the mole ratio of the other compound. So since we have N2O5 here, we're going to put moles of N2O5 here on the bottom. And then whatever we're looking for, we put on top, moles of NO2. And all we got to do is plug in the mole ratio, and that will allow us to figure out the rate of appearance for NO2. Okay?
That's basically.
That's it. You just multiply it by the mole ratio.
So we'll do the same.
Mm-hmm. What's up? So technically you could put a negative right here, and then you can put negative here since this is disappearing, and then positive right there. But when you're comparing the mole ratios, you can just keep them all positive and then just explain that if something is disappearing or appearing. Yeah. Okay, so what's the mole ratio between NO2 and N2O5? Yeah, 4 and 2. So it's 2 to 1 basically. And so all you got to do is multiply this by 2, and that will be your final answer. So you get 8.4 times 10 to the negative 7, and that's going to be molarity of NO2 per second. Okay, that's your rate. So basically what we went over is that the rates of appearance and disappearance can change over time, but also within a reaction, different compounds have a different rate of appearing and disappearing. Okay, so a lot of things to kind of juggle. So make sure that when you guys are doing these problems, you're labeling your numbers properly with the right chemical, with the right unit of measurement. Okay. All right. You guys think you could try one on your own real quick before we move on? All right, so we will move on to 11.6. So I'll give you guys maybe about 2 minutes to do 11.6. After that, we will move on to the final section for today. Take about 2 minutes to do 11.6 today. Okay, so hopefully this is not too bad. We got 6 times 10 to the negative 5 molarity of O2 per second. And then we just need to multiply that by the mole ratio. Now, the mole ratio is 3 moles of O2 for every 2 moles of O3. And so it's a 2 to 3 ratio. And so all we got to do is multiply this together, and that will give us our final answer. Oh, why'd I put a... Dude, it's that coffee, man. I'm just off my game now. Okay, 4 times 10 to the negative 5 molarity of O3 per second. And then, since it's disappearing, you can just write disappearing. or you can put a negative if you want. Okay, and that's your answer.
That was a beautiful thing. Look at that.
Thank you.
That's no. It's okay, the little back arrow.
Fancy
That's
schmancy.
like a Christmas card, like.
Thank you. Did you guys know I'm actually trying really hard to write neatly for you guys up here?
Really?
My actual handwriting actually looks like dog.
Like right.
Yeah, like worse than Brian. Yeah, so I'll just copy this down, okay? So if the rate at which O2 appears, this is what my real handwriting looks like. Yeah, I can read it. I'm just copying this right here. If the rate at which O2 appears in the I didn't finish writing reaction, but I don't know. They figured it out. Anyway, all right, last section for today. We are going to be talking about something called rate laws. And I hope that you guys love rate laws more than I do, because I hate rate laws. Okay, that's probably not a good way to encourage you guys to learn this, but rate laws. Yes. Yeah, that's basically the way they derive it. But you can just use mole ratio. Yeah, I'm trying to keep it simple for you guys. Yeah. It's like my AP Calc teacher always taught me. KISS, K-I-S-S. Keep it simple, stupid. Always remember that. Okay. So rate laws. Now I want you guys to write this general reaction right here. The lowercase a, capital A. I want you guys to copy it down. Because this is what we're going to be referring to write our rate laws. Okay. We are writing rate laws. Thanks. You guys are writing laws that have no power here. Okay, so make sure you guys write the general reaction, the lowercase a, capital A, plus lowercase b, capital B, and then the arrow. And then I want you guys to write the rate law underneath right here as well. So these two things. Okay, the general reaction, because the general reaction is going to determine the rate law. Yes. Yeah, M as in monkey, and N as in Nigel. Sorry, these are the first words that are coming to my head.
You know the what's that called? Phonetic?
No, I don't.
My stepdad does.
Doesn't he?
Military. Anyways,
Do you know what M is?
Mike.
Is it really Mike?
Yeah, it's Mike.
What's N?
And no, it's not. I don't know. And I'm trying to think of because he always like sometimes he spells out words and that's just how I know all of them.
No, it's very useful. Yeah. I just know tango, alpha.
Tango, alpha, beta.
I don't know.
Phonetic.
It's like what they use in the military to communicate in case like the signal's bad. Yeah. Zulu. Zulu is Z. I know Zulu. Anyway, whatever. Everybody got the rate law and the general reaction?
Okay. It's November.
November. That's tough. Anyway, yeah, I should learn that. Because when I'm on the phone and they ask me to spell something, because I use like the randomest words. I'm like, B as in ball, and they're like, mall? I'm like, no. So yeah, I should learn that.
You need to say words that like don't sound like what they actually say. Like
Or like the ones that are like silent.
yeah, like pterodactyl.
Pterodactyl. Yes, sir.
Yeah, pterodactyl.
Alrighty, guys. So let me show you guys or talk about how to use the rate law or how to write rate laws. It's pretty simple. Now, if you guys notice, there's a K in rate law. This is called the rate constant. Okay, and so it's going to be a constant for whatever reaction you're talking about. However, this K depends on two different things. Okay, the first thing it depends on is which reaction you're talking about. So every reaction has its own rate constant. And it also depends on the temperature. So every reaction has its own rate constant And every reaction has a different rate constant depending on what temperature it's at. You will not have to memorize this, okay? It will be given to you. However, one thing I do want to mention, and this is very important, is that the units of measurement depend on the overall order. Now, we'll talk about what that means next time, but this is why I don't like rate laws, because there are multiple different rate laws, basically different levels for these rate laws, okay? And it's a lot of math, so that might sound kind of weird right now, but you guys will see next time how annoying these can be. Okay, and then these numbers right here, m and n, those are exponents, okay? And they are typically small whole numbers, okay? Typically. There is actually 0.5, but for the most part, it'll be things like 1, 2, 3, okay? And these values tell us what individual steps happen during a reaction. So we'll talk more about these later. It'll make more sense as we do more problems, but just keep that in mind. And then A and B is going to be the concentration of your reactants, okay? So that's what the rate law is dependent on. It's dependent on the constant times the concentration of the reactants to the power of m and n, depending on which what order reaction it is. This right here?
No.
Top equation?
Yeah.
What do you mean? It's a generic equation, so we just use this as a placeholder so that you guys can see where we get our values. Yeah, so if, for example, it was something like this, let me give you a real one. CO2 plus H2O, and then we need to balance it. So there's 2 right there, and then 2 right here. So if this was the actual equation, the rate law for this equation right here is going to be the rate constant times the concentration of your first reactant to the power of m, and your second reactant to the power of n. So that's, yeah, this is like a placeholder reaction. Yeah, of course. What's up?
So the rates, like, based on reactants.
Wait, so what are the lower cases?
So those are your exponents whole numbers, small whole numbers, and we'll talk about how to find those in a sec. Yeah. What's up? So you're gonna have to figure out m and n, and we'll go over that in a second. Yeah. Alrighty. So basically, if you know the rate law for a reaction and the reaction rate, we can solve for the K value, the rate constant, and that is what we're going to be doing right now. So let's take a look at 11.7. Okay, there's kind of a big table, and I'm actually going to scroll down a little bit. So if you guys want to have this up on Canvas to look at the table, I just want enough room to do the math. Please make sure that you guys have this up on Canvas, okay? All right, so what we're going to do is we're going to use the table above and the rate law to find the value of K in these different experiments, okay? So what I want you guys to do is I want you guys to first see if you can write the rate law for this reaction, okay? So this is the chemical reaction. I want you guys to see if you guys can write the rate law for this reaction, okay? So write the rate law for this reaction. Mhm.
Oh, wait, no,
No, it's the rate constant. And I'll talk about how to find m and n in just a second, so just keep those as m and n. But I want you to find the rate law for this problem right here, okay?
So that's the rate.
Yes.
You have to know the K? Or should we-
We're calculating for K right now.
Oh,
Yeah. All right, guys, so for your rate law, you should have written that the rate is going to equal K, the constant, and then the concentration of the first reactant, which is ammonium, NH4 plus. And then for now, we're going to put M. And then the concentration of NO2 minus is the power of N. So that's the rate law, okay? So far, so good? Okay, now I'm going to show you guys how we get M and N. It's very easy. All we got to look at is the coefficient or the number in front of these compounds. So what's the coefficient in front of NH4? 1. So your coefficient here is going to be 1. And same thing for NO2, right? It's going to be 1 and 1. Okay, super simple. Okay, now I do want to mention sometimes it will not be the coefficient. We'll talk about those exceptions, but most of the time it will be the coefficients. I know. I wish I was making this up, but I'm not.
Sorry, I completely misruled out the ones.
The coefficients in front of
okay.
the compounds, yeah. But it's not always going to be the coefficients, and we'll talk about those exceptions later.
Exceptions.
Not octet. Yes, on the balanced chemical equation. Yeah.
Like, it says like initial NH4, you put that number in where you wrote NH4, right?
Yes, yes.
Okay.
Okay, so let's solve part A. Oh no, okay. So part A, we are finding the K value for experiment 1. And so what I'm gonna do, just to make our lives a little bit easier for the math part, is let's rearrange this equation so that we're just solving for K, okay? So if I'm gonna isolate K, what I can do is I can just divide by the concentrations of our two reactants, and then that will give us K. So we can rearrange this reaction or this equation to be the rate divided by the concentration of NH4 plus, and then power of 1 is just the same thing as the value that we have, and NO2 minus. Okay, so if we have this equation, it'll be a little bit easier to solve for the K value. Yes.
Why do we use brackets instead of points?
Brackets means concentration. It's just typically how they communicate that. Okay, so with that being said, I'm gonna give you guys about 3 minutes. See if you guys can calculate the K value for experiment 1. The data is up here for you guys. And the K value for experiment 3 as well. And see if you guys can see if changing the initial concentration affects the rate and the rate constant. Okay, both of them. Yes, the brackets mean multiplication.
Yeah.
They mean concentration, but for the math operation, we can just consider them parentheses. Yeah. Okay, so see if you guys can solve for K for experiment 1 and experiment 3. And then just based on the numbers that we get, I want you guys to figure out if changing the concentration of reactants affects rate and the K value, rate constant. Okay, so I'll actually give you guys about 5 minutes to do that. And then, yeah, we'll go over it together. Okay, guys, let's bring it all together. So for part A, we want to find the K value for experiment 1. So I'm just going to plug in my values. So K is equal to, can't hear myself think. Okay, all right.
Yeah.
It's not the coffee. I spilled the coffee. I'm so stressed out by that still. Okay, so the rate in experiment 1 is 5.4 times 10 to the negative 7. Now we got to write the units of measurement, which is molarity per second, okay? And then we're going to divide that by the initial concentrations. So for NH4 plus, it's going to be 0.01 molarity. And then for NO2 minus, it's going to be 0.2 molarity. Okay. So far, so good. Okay. So from here, you just need to just do regular math. And so I'll give you guys the final answer. You should get 2.7 times 10 to the negative 4. Everybody got that? If you got a different exponent, make sure you guys get it in correct scientific notation. Well, you should get 2.7 times 10 to the negative 4. Now, yes.
They're gonna mark you down if you don't put in scientific notation.
Yeah.
Okay.
Yeah. All right. So we did the numbers. Now we got to make sure we get the correct unit of measurement. Okay. So for the unit of measurement, we got to cancel out the values that we have. So I'm going to erase the numbers just so that we can look at the units of measurement a little bit more easily. And that way we can figure out what the heck this is. Okay, so if you got molarities on top and molarity on bottom, what do? They cancel out. So this molarity will cancel out with this molarity.
For seconds per meter.
Okay, however, if you guys notice, so you have per second, but you also have per molarity because both of them are on the bottom of the fraction. So the unit of measurement for K here will be molarity -1 and second -1. Per molarity per second.
Yes. Also do like second.
So you can also write the unit of measurement like this: 1 molarity second.
You can't just like flip it.
No, because molarity is on the bottom. You can't flip the fraction. You can only do that if it was 1 over molarity on the bottom.
Second divided by polarity, it's like it's like polarity on top of it.
Does it get this as your unit of measurement? No, it should be /SM. So the other way you can write it is it has to be /S times M because there's still a 1 on the top. These are both underneath the fraction. They're both denominators. So no, I think. So.
What does that mean?
So yeah, it's kind of hard to visualize what that means. And that's why it's a rate constant. It's just a constant that helps us balance out this reaction. It's what allows us to take molarity here, and make sure that it's equal to molarities per second. It's basically a way of balancing out the units. Yeah. All right. Any other questions about that one? Okay, I'm gonna give you guys the rate constant for experiment 3, or just right off the bat. And it's gonna be 2.69 times 10 to the -4. Same thing, per molarity per second. Okay. So very, very similar. Okay, so let's take a look at these two experiments and then compare them, and then we'll be all done for today. Okay, so we got experiment 1 and we got experiment 3. Okay, now if you're comparing the two experiments, what happens to the reaction concentration between the two? Yeah, they go up, right? So we can write the what is it? The comparison right here. So as you increase the reactant concentration, okay, so if you increase the reactant concentration, what happens to the rate? Yeah, the rate increases, right? 21.5 is bigger than 5.4. And also just based on what we learned before, right? If you increase the concentration, the rate's going to increase, right? However, if we take a look at the two K values, what happens to the K value as you increase the reactant concentration? Yeah, it gets smaller. I know it's just a little bit smaller, but it still does decrease. Okay, so K will decrease. So this is the relationship that you should see between the two. Okay. Alrighty, guys. So before we finish up, we're all done with the new stuff. I do want to mention one thing real quick. Make sure that you guys keep the units of measurement in mind, because K is not always this unit of measurement. Okay, so K is not always this. Okay, K will not always be molarity per molarity per second. Okay, it's gonna depend, and you guys might be able to tell, but depending on what these exponents are, it's going to change what the units of measurement are. So just keep that in mind. Be aware that the unit of measurement for K does not always stay the same. It's going to change depending on what reaction we're looking at. But that's what we'll do next time. Okay? Woohoo!